up? Mr. B here again, bringing another sweet, wicked, awesome math video. This video I'm going to take you through some critical numbers and basically being able to find the critical numbers of a polynomial and then using that then to figure out if those critical numbers are max and mins. So in my calculus class right now, we're about to start graphing using derivatives. So this is like an introductory video for my class, but if it helps you too, then that's great as well. So critical numbers are basically possible locations of max and minimum points on a graph. Up until this point, you've probably graphed polynomials and you've looked at the x-intercepts, the y-intercepts. Maybe you've looked at the end behavior, leading coefficient, negative, positive, that kind of stuff. But you haven't really looked at where you have a max or min point on a graph. For example, a cubic has a maximum and a relative minimum. Relative mean in the area of a set number of points. Anyway, we'll talk about that a little bit. So a critical number allows us to be able to find that those max and mins. So basically a critical number is a number that's in the domain of f of x that makes the derivative equal to 0, or it makes f prime of f prime of c not exist. So that won't happen with polynomials. So for us, we're going to focus on when the derivative is equal to 0. But if you have a more complicated function like a rational function, then it's possible that it might make the derivative undefined. So it's also important to remember that critical points are possible max and mins. We have to prove that they are max and mins by looking at the intervals of increase and decrease. And we do that by using the first derivative test. So basically what the first derivative test says, and I always like to draw this out. It's always a little bit easier to sort of explain by drawing it out. So if you have a function that is increasing and then goes to decreasing, that has a max. And the opposite, if it's decreasing, then it goes to increasing, that's a min. And you can kind of picture this as like a little cubic, increasing and then decreasing, and then you have your max and your min. Well, the first derivative test allows us to determine if something's increasing or decreasing, and then in turn if it's a max or a min. So if something's increasing, we know that its first derivative is positive. So if I take a number in that range, I put it into the derivative and it gives me back a positive number, I know that function's increasing. If the derivative is negative, I know it's decreasing. So if the derivative goes from positive to negative, it's a maximum, or increasing to decrease. And the opposite's true for a minimum. If the derivative is negative or decreasing, the function's decreasing. And then if the derivative goes to positive, then that means, of course, we have a min. Right? So we can get a lot of valuable stuff from that first derivative in terms of being able to tell the relative extrema. And the relative extrema is just a fancy word for max or min. Now, sometimes we'll use the word relative extrema because sometimes, like in a cubic doesn't really have a max or min. It continues up or down in the y direction to infinity and negative infinity, but they have relative extrema. So in a certain area, like for example, if I was to draw this cubic, that's a relative max. It's not the maximum because this graph just keeps going up and up and up and up, but it's, in the area, it's relatively the maximum point. So that's what it means by relative extrema. It's not the absolute max, but it is in a small area, it is the largest point. So we've got a function here, a cubic, and we're asked to determine the critical numbers, the intervals of increase and decrease, and then the relative extrema. So we're going to do that. Okay, so first thing we want to do when we're given a question like this is find the derivative. Now right now we don't know anything about the second derivative. We'll talk about that in another video, but right now we're going to find the first derivative. But in general, if you were going to graph this guy, the second derivative would also be useful. So we're going to use the power rule. So the 3 drops down, multiplies 2, we get 6x minus 1/2. We get a squared, just like that. And then plus, so 2 times 5 is 10x minus 1, so 10x. The derivative of a linear term, so 4x is linear, is just the coefficient. and the derivative of a constant, -5, is just 0. So there's my derivative. Okay, so we've got that done. So now let's look at determining the critical numbers. So remember, critical numbers, I'm just going to call them crits. The critical numbers are where the derivative is equal to 0, so y prime equals 0, or y prime is undefined or does not exist, whatever you want to say. So division by 0 essentially is when that comes in, right? Which we don't, or it could be, if it was a root, could potentially be like a radicand, that'd be negative. So we don't need to worry about this part for a polynomial derivative because of the fact that, you know, it's continuous everywhere. However, we will we'll have another video on it because rational functions is probably what you're going to deal with mostly in calculus anyway. So, but regardless, we're going to take this and we're going to set it equal to 0. Now this is just a quadratic, so you need to figure out a way that you're a ninja at solving quadratics, whether it's factoring, if possible, or quad form. Anytime I go to factor, though, I always want to look for a a common factor. So 2, and I'm just going to divide through. Since it's equal to 0, I'll just divide through by that 2, and I don't have to worry about putting it out front. Okay, so I'll put that as 5. So now the next step, I didn't divide the last number. I know you guys are screaming at the screen. The next step is now to be able to factor this thing. So it's what adds to give us 5, so the middle number, and multiplies to give us 3 times 2, which is 6. So I'm going to use something I call the Barnes method. Every teacher's least favorite factoring method, but my students like it. And it's very similar to, well, the first step is similar to decomp, but then after that it gets a lot easier. So we got to first of all figure out the numbers that make this work. So it's x plus 2 and x plus 3. So 2 times 3 is 6, and 2 plus 3 is 5. So then the next step, what we're going to do is we're going to take whatever it is our most recent leading coefficient is. So in this case, whatever's in front of the x squared is 3, and we divide both of these by that leading coefficient. So I end up with, if I can reduce the fraction, I do, but if I can't, then that 3 just comes right up in front. So 3x plus 2, and then x plus 1, and that equals 0, of course, because that's what we had originally. So that's our factored form. Again, you can do that with decomp, quad form if you really wanted to, or you can use this, which I call the Barnes method, also known as Joe's method if you're looking for another video, but it's some on my YouTube channel as well you can watch. So we solve each one of these. So this one's easy. That's just -1. This one's going to require a little bit more work. Maybe you can see it, maybe you don't. But we have to subtract 2 from both sides and then divide by 3. So we end up with x equals -2 over 3. So these are my 2 critical numbers. Okay? Just looking for my binder for 1 second, guys. So yeah, so these are my 2 critical numbers. So what they allow us to do now is determine if they are possible locations of max and min. So we would expect that at -1 and -2 over 3, there's something happening. Could be a max, could be a min, maybe it might be nothing. But with a polynomial, there's going to be something happening. Okay? I'm going to slide my head out of the way here. All right, so next thing we do, in order to prove a max or min, we have to do intervals of increase and decrease. So intervals of increase or decrease, and that's how I represent increase and decrease with those arrows. All right, so all we do for increase and decrease is we make a number line, -1, -2 over 3. So my crits go on the number line, and we label this as f prime. The whole purpose of this number line is to determine if the derivative is positive or negative in each interval. So there's 3 intervals, right? So this one right here, that first interval, this one right here, the second one, the middle, and then the end. Now, when you have a quadratic, things are really, really good, All right, so I'm going to show you how to deal with a quadratic derivative that makes our life a lot easier. So we know that this quadratic has an a value equal to 3. So that's a positive a value. A is greater than 0. That means that the graph opens up or looks like this. So if you were to graph that derivative, it would have two x-intercepts. They would be -1 and -2/3. So I can actually dot this quadratic on here just like that. I don't know why that random line is there. So you can dot that quadratic in just like that. And that then tells us where the graph is negative and where the graph is positive. So anywhere the graph is above the number line, which is technically the x-axis, it's positive, so it's plus. In between it's minus, and then here it's plus. So if you have a quadratic derivative, it gives you two x values or two critical numbers, you know that it's going to be a either plus minus plus or negative plus negative based on opens up or opens down. This one's opens up, so it's plus minus plus. If it opened down, it's minus plus minus. So we've confirmed that this graph has a max and a min. So if you look at this, remember positive means increasing. The derivative is increasing, and then it goes to decreasing. So this represents a max. The derivative goes to plus to minus, increasing to decreasing. And then remember, the increasing and decreasing, that's our original function. That's what y is doing. Okay, and then over here we're increasing. So we go decreasing on the original graph to increasing, and that means we're at a minimum. Okay, so we have a max and a min. So those are the actual values. Now the last thing that we want to do is we want to write out, so step 4, our actual max and min points. All right, so the y values essentially. So one thing I want to make a really important note is that y values come from the original. I can spell it right, from the original. So what that means is that original y equals is where all the y points come from. Do not go back to the derivative. If you go back to the derivative, it's going to give us 0 because that's what we found those values come from, right? So our max is x equals -1. We're going to go back to the original. So we get -2x cubed plus 5x squared. So not negative, positive. 2 -1 cubed plus 5 -1 squared plus 4 times -1 minus 5. So I'll run the mental math on this. So that's -2 plus 5 minus 4 minus 5, so that ends up equaling -6. So if we were going to plot this graph, we would have a max at -1, -6, and that's where the y value comes from. So for the min, we're going to do the same. Now this min is not mental math friendly, so I'm just going to go through the motions with this one. So 2, and then we put -2/3 cubed plus 5 times -2/3 squared plus 4 times -2/3 minus 5, and if you run the numbers on that, I got it written down here, so I got my notebook out, 163, not 67, over 27. So, and that's a negative, yeah. So again, that if I was making up a test for you guys, I would make the numbers work out a little bit better than that. But sometimes, you know, if you're doing a textbook question or something, they don't really care about mental math, that's what you're going to end up with. So guys, this is one of those topics that you just need to practice until your arm falls off. And you got to increase the difficulty level with the function. So start with polynomials and then move on to rational functions that are different, that have like some with a root. Maybe you get a quasi-rational function with a root. Highest power on the bottom, highest power on the top, equal powers, oblique asymptotes. There's lots of different types out there. Alright guys, as always, thanks so much for watching. If you stuck around for the whole video, feel free to like, share, subscribe, all that fun stuff. I'm trying to grow my channel. I'm back in the game, so appreciate all the support. All right, everybody. Thanks a billion. See you guys in class. Peace.